record this, so I will. Okay, here we go. So we need to graph the systems of linear equalities here. So we have two different graphs that we need to try to get on our page here. And so this first graph here, we have negative x plus 2y must be less than or equal to, or greater than or equal to, excuse me, negative 4. And then the other pieces of information we're told there is that x can be any real number and y can be any real number. So that means we're going to just shade in the entire region of correct answers. So what I am going to do in this case, Sarah messaged me and asked, she said, do you prefer y equals mx plus b, or do you prefer intercept form? Personally, I like y is equal to mx plus b better because it gives you more information. But for the purposes of today, for teaching you how to do these questions, I'm probably going to do exclusively intercept form, where what we do is we just set x equal to 0, y equal to 0, and then figure out the point where that becomes equal. So what we have here is we have x plus 2y is greater than or equal to negative 4. And so what I'm going to do is I'm going to set x equal to 0. So I have 2y, and I need that to be somehow equal to negative 4. That would mean if I divide both sides by 2, that would mean that y would have to be equal to negative 2 in order for this this statement up top here to be true. So at x is equal to 0, y will have to be equal to negative 2. And then if I want to find the x-intercept, I would take and make y equal to 0. So negative x is greater than or equal to negative 4. I want these two to be exactly equal. That'll tell me where the intercept is. So again, if I have just a 4 for x, then what that allows me to say is that negative 4 is in fact greater than or equal to negative 4. So I would know then that my intercept is right at this point here. And then I'm just going to draw a line through those 2 points. Oops. Let's try like that. So something like that. So that's our first graph there. And I'm going to put a little black dot by this just to show you that that one was done in black, because the next one we're going to do that one in red. And this equation says that y must be greater than or equal to x. If y is equal to x, let's take this situation where y is equal to x, then whatever y is, x must also be. So that tells me that in terms of the intercept, I know it's going to go through the point 0, 0. I also know it'll go through the point 1, 1, 2, 2, 3, 3. It'll go through all of those x, y points because y is equal to x. So what I want to do is draw a line from this very corner of the graph, this very top corner here. Fix this. Just like that. So those are our two graphs there. And then what we can see, and I actually need to fix this one a little bit here. Okay, and what we can see is that we have a point of intersection right down here. So what is important is that your graphing is accurate, because as you saw, like if this line is sort of on the points but slightly off, the point of intersection moves down and it's not actually where it needs to be. So I need to have this graph be almost perfect in order for this to work. And what we were told is we were told to fill in the point of intersection as a solid dot if it's included in the solution set. So both lines are solid. And in this case, we have greater than or equal to's in both case. So what I can do then is I can fill in this point here of intersection as a solid dot. That's where the two lines are intersecting. And then what I want to do is I want to check a couple number of values, because I have 4 different regions. I have 4 different regions that could be correct answers. This is the first region up here. That could be all of the correct answers up in that area there. Second region could be down in this little quadrant down here. We don't know if the answer's in there. Third region could be, well, just below both of those graphs. And then the last region could be in here, in between those two lines. So we want to pick a point, and we want to use our heads a little bit to be logical about which point we're choosing. in terms of where do we think this graph will fit? Where do we think this graph will fit? And so I know a couple pieces of information. The most important one that I know is this one right here. This equation tells me a lot of information. It tells me that y must always be greater than or equal to x. If y must always be greater than or equal to x, well, this line here, this red line, was the graph of y is equal to x. So if y must be greater, that means it's got to fill any of the area above this region here. So that leaves us with two possible solutions. That leaves us either with this top number 1 and number 2. And, hello, that was not what I wanted to erase. So that means I can get rid of both the 4 and I can get rid of the 3. And what we would want to do now is we would want to look in this bottom second region and we would want to test to see if this point, for example, here is fitting within both of those solutions. So previously we only tested it in one equation. Now we need to do our tests, in 2 equations. Okay, so we are going to choose the point negative 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8. 8. So we chose the point negative 9 comma negative 8. And so we're going to plug it into this first equation here. And we're going to see if that works out. So x value, we're going to plug in a negative 9 for x plus 2 times negative 8. And we want to see if that's greater than or equal to negative 4. So we have negative 9, which negative of a negative, that turns into a positive 9. This turns into negative 16. And we want to check if that's greater than or equal to negative 4. As it turns out, negative 7 is not greater than or equal to negative 4. So what that means is that our solution cannot fall within region 2. We've already confirmed that because that black point there did not work for this equation. So we know then, in fact, that it will be falling all within this first region. And so we could shade in everything above the point of intersection and also above this red line here. Just like so. And then I don't need to put any dots on this equation as we did in the previous lesson because these statements here tell me that x can be any real number, meaning that any decimal, any fraction, any positive or negative number, they all fit within this schema. And so what I want to do now is I'm going to pull up a program called Desmos. This is a really great program if you want to check your solutions. And so you can pull up on the little keyboard in the bottom left here, and it'll give you a bunch of these different symbols. The first equation that we were given was negative x plus 2y, and we said that that was greater than or equal to negative 4. And as you can see, there's the graph there, but it also shows us the region that would have been shaded. And we said that we knew that based on our answer, which we saw right here, we said we knew that it had to be above the black line. And we've actually confirmed that by graphing here. And then if you click on the little number 2 below it, it'll let you graph a second equation. And that second equation was that y is greater than or equal to x. And now if we look at the graph, and let me zoom out a bit here. I don't want to do that. Let me just zoom out. You can see that we have actually shaded in the region of the blue and the red, so this purple kind of area up top. That fits in with both of the points on our graph. And then if we zoom in, this little point of intersection here is at negative 4, negative 4. And interestingly enough, on our little graph, that was also our point of intersection, or it should have been anyways. 1, 2, 3, 4, 5. So I drew my graph really poorly is what that means. 1, 2, 3, 4, 5. So I drew my graph poorly, but we had the point of intersection of negative 4, negative 4. I think it's in pre-calc 20. You would have learned a couple different ways of solving these and finding that point of intersection. You can use Desmos, and in fact, what the government of Saskatchewan wants you to do is they would have wanted me to give you technology. That's what a lot of the textbook is based off of. There is a way to solve. There is a way to solve for these system of inequalities by not using any computer program or anything like that at all. Basically, what you end up doing is you try to get the same variable on the same side and try to make these two equal to one another. So I'll show you really quickly what I mean by that. So we have two equations. We have two equations like this where y is equal to x, and we have negative x plus 2y is equal to negative 4. I'm going to choose the equal sign instead of the greater than sign because I want only one solution. And so there's two ways you can do it. You can do it either via substitution or you can do it via elimination. And so the idea is you want to get y and x on opposite sides of the equation. And in this top one here, we see that y is equal to x, meaning I can simply take this second equation here and I can just plug in y in place of x because I know that those two have to be equal to each other. And then I can solve this and I have 1y is equal to negative 4. And I would be able to figure out that my y point of intersection would be negative 4, which was confirmed on our Desmos graph. And then if we know that y is equal to negative 4, if we know this value is true for our point of intersection, we'd take that and plug it back into our original equation. So you could say negative x plus 2 times negative 4 must be equal to negative 4. And then you'd have negative x plus negative 8 is equal to negative 4. Add 8 to both sides. You get negative x is equal to positive 4. You would have to get this negative sign, get rid of it, so divide by negative 1. Sorry, divide by negative 1, divide this side by negative 1, and then you get x is equal to negative 4. And we'd have our point of intersection as negative 4, negative 4, which was exactly what we saw in this Desmos graph. We saw that the point of intersection here was negative 4, negative 4. So that was substitution that you can use to solve and actually figure out the point of intersection. But for the purposes of Foundations 20, all we're concerned about doing is, can you take it and plug it into a calculator or a formula, or can you roughly graph it and figure out the point of intersection? And so we use Desmos. I would have given you a graphing calculator if you were in the classroom, and we could go from there. So that's question 1. Does anyone have any comments, questions, concerns about example number 1 there? Okay, lovely. Let's move on to example B. Example B, we have two equations again, as we will with all of these different questions. And again, what I'm going to do is I'm going to do this top one, all of those information in black, this bottom one, all of that graphs or all of that equations information will be done in red. And so we're going to do the exact same thing that we did last time. I want to be able to figure out the two intercepts for y is less than or equal to negative 3x plus 6. So what I would do here first is let's set x equal to 0. If x is equal to 0, then we have y is less than or equal to 6. So that means that my intercept on this particular graph would be 1, 2, 3, 4, 5, 6 right there. And then if I want to find the x-intercept, I'd set y equal to 0. So 0 must be greater than or equal to negative 3x plus 6. I would subtract 6 from both sides of this equation. We have negative 6 less than or equal to negative 3x. Divide both sides by negative 3. And then we would get x is equal to 2. So we would know that our x-intercept there would be 2. As I said, I'm doing just intercept form just to keep things fairly straightforward and simple for us rather than doing mx plus b over and over again. And we're going to move these two lines and try to get them to line up almost perfectly here. Let's see what we can do. We can get it kind of close here. This is where using Desmos becomes a lot more functional and a lot easier than me using OneNote. Okay, that looks about right. So there's that first line that we have there. And then the second line that we have, I drew a solid line because we have this equals sign. The second graph, we do not have a solid line. We have a dotted line. And that is a point of information that we need to for sure be paying attention to. So y is greater than 1. So that means at all times of this graph, y can't be equal to, and this should be done in red, my apologies, but it must be greater than 1. So we need to draw a dotted line because it's not equal to 1, it's just bigger than 1. So we draw our little dotted line here like this, and we could draw our 2 points like that. Awesome. And what we want to do in this case is because one of the graphs is not equal to, this point, our point of intersection, which I'll do in blue, needs to be drawn with a hollow dot, a dot that is not filled in, because this second equation here is not equal to, it's just greater than. So then the next thing that we need to do is we need to look at our two equations and figure out what quadrant of this graph or what quadrant of these two intersecting points we want to fill in. So we have quadrant 1, 2, 3, or 4. We can fill in either one of those 4. I would immediately go to this second equation here and see y must be greater than 1. I know for a fact then that that has to be going up from this red dotted line. And so as such, I'm going to just eliminate 2 and 3. I know that those two are not the correct solution here. The next thing that I would do is I need to test out this second graph. I need to figure out what side of this graph I would normally shade in. And so I'm going to choose, I like this point right here. I like choosing positive x values and positive y values. So anything in this top right quadrant here, I like choosing values from there because they're a little bit easier to plug in. So we want to check to see if y is less than or equal to, the point I chose there was the point 3, 2. So I want to plug in my numbers there. I want to plug in the 2 for the y, and then I have negative 3 times 3 plus 6. And I want to check to see if this negative 2 value is in fact smaller. So positive 2. Must be less than or equal to, this would be a negative 9 plus 6. 2 is not less than or equal to negative 3. So what that means is I know that it's not quadrant 4 that needs to be shaded in. I know that it's not quadrant 4 that needs to be shaded in. I know that it's quadrant 1, this top right hand or top left hand quadrant here. For some reason when I'm looking at my screen I get my directions confused. Okay, so I want to shade in all of that region. I'm not yet done this question, and that was because I have kind of neglected up until this point this last little piece of information over here, where x is equal to any integer and y is equal to any integer. And what we said last time, these points here are going to become really important to you to have those written down or have those saved somewhere. Integers are positive or negative whole numbers. This would have been a little awkward if it was just whole numbers, because then we'd only have a little positive region there. But because it's positive or negative whole numbers, what that means is I can start to put little dots all the way around here. I am not going to put any dots. I'm not going to put any dots along the red dotted line, because as we said, that red equation there, that y is greater than 1, we said that that one never equals exactly 1. Because it never equals exactly 1, I can't put a point on that red dotted line there. That would be inaccurate of me to do. So there's lots of little niche things that you need to be paying attention to when you are graphing these linear inequalities. There's lots of things that I'm looking for to see if you make a mistake on, or to see if you forget to do one or another thing. I would also fill in any of these values here because they fit within, and then I'd also fill in this value. So we can check those two equations on Desmos and just confirm that we were in fact correct. The first equation was that y is less than or equal to negative 3x, negative 3x plus 6. That's that graph there. That looks about what we graphed previously, so that's good. And then the second equation that we had was that y is greater than 1. And we can see that the overlap of these two equations exists over here. We see that the point of intersection is actually not a solid number. It's a decimal point of some sort. But that would be our point of intersection there. And like we said earlier, with our graph, we're going to use a hollow dot because this second equation is not equal to 1. It's greater than 1. Okay, so there are our first two examples. We have one other example that we're going to go through here, and then a couple word equations as well. Okay, so for this last example, a couple pieces of information that we want to pay attention to. Again, I'll do this the same, black and red. A couple of pieces of information we want to pay attention to are, we have two equal sign, greater than or equal to or less than or equal to signs, which is important for us to realize. Other piece of information that's important for us is these x-ENs and these y-ENs. And what those mean is that x is going to be equal to any natural numbers. So that's positive integers that do not include 0. Positive integers that do not include 0. Okay, let's do this first graph here. So this first one, we want to find the intercepts again. So if we set x equal to 0, we know that y must be greater than or equal to 2. If we set y equal to 0, we know that x must be greater than or equal to 2. And so we know that y-intercept will be 2. X-intercept will also be 2. And then looking at the second equation here, we have x must be less than or equal to 4. And so I would count up 1, 2, 3, 4. I know that it's going to be less than or equal to, so on the left side, going that way, of that point there. So I'm going to draw a straight line down. And I'm going to move this one over here, just like that. Erase these two little arrows that I drew, and then I'm going to fill in this line here like this. This and slightly off still. This and like that there. It's pretty close to how it should be. We can see our point of intersection where the two lines are crossing. And key feature again we said about this graph or about these two equations is that that is an equal sign and that is an equal sign as well. It's a greater than or equal sign up here, a less than or equal sign here. So what that means is that our point that we put on this graph must be a filled in solid point, and it's right there is our point of intersection. So again, we get left with our 4 choices. We have 1, 2, 3, or 4 choices to deal with in terms of where we will be shading. I would again use my brain a little bit and look at this equation here. X is less than or equal to 4. And what I would realize is that if all x values are smaller than 4, the graph must only fill in that side. So if I were to fill in the red region, I would only want to fill in the left side of this graph. So I can erase my 4 and my 3, and I can deal with those in a second here. Now what I need to decide is I need to decide if region number 1 or region number 2 are the ones that I actually want to fill in. And so I will do so by checking and picking a point. And I am going to choose this blue point right here. That blue point is x value of 2 comma 1. X value of 2, y value of 1, and we're going to test it by plugging it into this first equation here. So we're going to see that 2 plus 1, is that greater than or equal to 2? 3 is in fact greater than or equal to 2. So I know that it works for the 1 graph, And I also will know, I don't actually have to check this red graph. I know that it also works for this red graph, the red line as well, because it's on the left-hand side of it where we said that x is going to be smaller than 4. So I've actually discovered what region it is. It's this upper region here in quadrant number 1 that I had drawn. So I'm going to fill in, I'm going to highlight all of this area, but before I do, I need to revisit these two. Ooh, that's not a straight line at all. I need to revisit these two little points here. And those say that y and x can only be natural numbers. And we said that natural numbers were positive integers that did not include 0. And so as such, I'm going to fill in only this region here. I'm going to fill in only this region here. We said that anything with the xen, yen saying that it's a natural number, we said that those numbers must be positive whole numbers or positive integers that do not include 0. And so what I need to do then is I need to fill dots in at all of the positive spots. And I'm not going to put it along the y-axis here because we said that it cannot equal 0. Sometimes this math class feels like I am Bob Ross, just drawing little dots and narrating along to myself. And you get to follow along with my really poorly drawn drawings. Okay, so that is 3 examples of linear inequalities. I'm going to just pause this recording